All right, this is worksheet 1 from your Unit 6 torque packet. This is just torque and equilibrium problems. And the first problem is the most basic example you get. It's a seesaw, and the fulcrum's right in the middle, and you have a lighter kid a little bit farther away from the fulcrum and a heavier kid a bit closer. First question asks, in like a scenario like this, how would your FBD look, right? So if I had an FBD for the beam, how would that look? And, hopefully this is... there's some obvious forces, right? So if this is our axis of rotation, right at the center of mass of the beam, remember center of mass is kind of like the point where you can say gravity acts on, right? Because really in reality, gravity is acting on each individual piece of the seesaw. When you kind of take, not really the average, but when you look at it as kind of like one object, the center of mass is where gravity is acting at, right? It's kind of where the mass, the center of the mass is located, I guess it's kind of the best way to put it. So first obvious force is, the center of mass, which is the middle, because this is a uniform beam, there's going to be an FG, right, by the earth. What's another obvious force? Well, the kid, right, there's going to be the force by the kid, and in my last torque problem, I talked about how it's not, like you don't say, like if I were to label this force, like let's say right, is it on the end? Yeah, let's say it's at the end, right? So you would not call it FG, it's really a push force, right? Like an FN, it's a normal force by the kid. But then when you draw an FBD for the kid, so if I were to draw an FBD for the kid, right, this FG and this FN, right, they're equal because the kid is not accelerating. So this FN, by Newton's third law, right, that's the same force. That would be equal to the FG of the kid. So yeah, there's going to be another FN by the other kid, right? So it's going to be a little bit bigger. It's a little bit heavier. So the kid will be pushing a little bit harder. And there's going to be, finally, right, if this was all of our forces, this whole beam is accelerating downward. What's the upward force that's not causing any acceleration? It's going to be the force by the fulcrum, which is going to, not to scale, right, it would be way bigger. It would have to balance out all the three forces that are downward. Okay, let's just write some F net equations for part B. So for the beam, F net in the x direction, well, that's just 0, right? There's no forces. F net in the y direction, there's also, it's also 0 because it's not accelerating, but you're going to have Fn, let's say Fn F, I guess. Yeah, Fn-F by the fulcrum minus Fn1 minus Fn2 minus Fg. For part C, now we have to write a torque net equation. So here's the cool thing about torque, and you will see this in the other problems. You can choose your axis of rotation anywhere. Just as a reminder, the general equation for torque, I guess I'll put it up here. Tau is equal to F times R, the distance from the axis of rotation, and another variable that we'll talk about in future videos, but it won't apply here, right? We can use this equation for these problems. So, you could choose any axis of rotation, and wherever you put your axis of rotation, if you have any force acting at that axis of rotation, it's not going to produce any torque, right? R, the distance from the axis of rotation, that variable would be 0. So if my axis of rotation is dead straight in the middle, Fg and Fn don't produce any torques. The R in that equation is 0. So if I were to write my torque net equation, and in this class, you only have torque in like one direction, right? Counterclockwise, clockwise. There's not really a y direction or x direction, at least in this class. So torque net is going to equal the torque by Fn1 minus the torque by Fn2. So I'll say torque by Fn1 minus the torque by Fn2, which is 0, because this thing is static. It's not rotationally accelerating. 0 Newton meters. How did I decide which one's positive and which one is negative, right? Because they're both pointed down. Which one causes a clockwise and which one causes a counterclockwise torque. You can literally use your pencil, like on the exam, on the AP exam, on your mechanical engineering test that you'll take when you're in college. You could just be like, okay, this is my axis of rotation. This causes counterclockwise torque. This force causes clockwise torque. So I know I could say counterclockwise is positive, clockwise is negative. Part D, person on the left has a mass of 70 kilograms and the person on the right has a mass of 90. If the person on the left is 1.2 meters away, how far would the person on the right be? So, old school Unit 2 stuff was like, hey, let's use our force net equation. Well, I only know the forces of Fn1 and Fn2, right? Because I know the masses, I know mg is equal to Fn1. That wouldn't be a problem, but hey, I got two unknowns. And there's not really another way I could solve for them unless I use the torque net equation, because then I have my unknowns, right? So if I go 0 Newton meters is equal to Fn, or torque by Fn1, which I'm going to say as Fn1 times R1 minus Fn2 times R2. Add both sides, and I'm going to replace these with mg, right? So m2g R2 is equal to m1g R1. The g's cancel out. You can cancel them out if you'd like, or you could just you could just plug in and do whatever. You essentially get 70, so I'm going to cancel them out. 70 kilograms. So G, I just canceled them, right? So R2, it would be 1.2, I think. Yeah, 1.2. Because this is stuff from the left side. Equals 90 kilogram in R1, and this is what we're solving for, R1. And I when I did this, when I got R1 is equal, R2 is equal to 1.07 meters. And I should have a calculator somewhere. I don't know where it went, but hopefully that's right. The seesaw has a weight of 250 newtons. What is the force that the fulcrum is applying to the seesaw when both people are on top? So this is where you use your torque net equation, right? So I can add, so if I say 0 is equal to all this stuff, I can add these three to that side. I get Fg plus Fn1 plus Fn2 equals Fnf, right? The force by the fulcrum. So 250 newtons is the weight, plus Fn2 is going to be 70 kilograms times 9.8. I'll use 10. On the AP exam you can, so might as well just save my, and I have a calculator, so it just makes it a little bit easier for me. 90 kilograms, 10 equals Fnf. So that gets Fn, the force by the fulcrum is going to be approximately 700 plus 900, that's 1600 plus 250 should be 1850. And I got, yeah, 1850. Perfect. So let's go on to the next one. We got like a little scenario where we have like this beam being supported by two strings, and we got a block. So if we were to draw this FBD, right, for problem 2, let me just draw this out, right? So this is the scenario. We have a block, and that's like what, 3.5 meters, and then this is A and B. For your FBD on the beam, right? There's going to be that FG, I think, unless this is massless. It's not massless. So there's going to be that FG at the center of mass, and if it's uniform, you can assume that's going to be in the middle. So yeah, FG is going to be at the middle. We're going to have the FN by the block, so I'll call that FN, just because there's no other FN, so I might as well call it FN. And you're going to have this tension by FA, I'll call it FA, why not? And then we have FB. Now, this is interesting. Are these going to be equal? Are these forces going to be equal? We would have to use torque to figure that out. So, I'm going to skip over the Fnet and torque stuff. Should I? Actually, I'll go through it. So, okay, I'll skip the Fnet. Hopefully, you kind of get that it would be FA plus FB minus FN minus FG would equal 0. For torque net, you can, once again, you could choose an axis rotation let's just go ahead and choose, let's just choose the middle. Why not? So right here, I'll choose this middle. So the torque by Fg, wait a minute, that's 0. So I don't even have to worry about that. So Fn is going to be counterclockwise. I'll say that's positive. So plus the torque by Fn. And then Fb is also counterclockwise. So I'm going to say plus the torque by Fb, sorry. And then hopefully you can see torque by Fa would be minus the opposite of, it would be clockwise. So Fa equals 0. And the next question asks, hey, which wire will exert a greater force? So the way you got to kind of go about this is use your torque net equation, right? So first of all, we should note that this distance, I'll say R is the same as this distance, right? Because they're both at the ends. And if our center or our axis of rotation in the middle, same distance. So we got the, they're both the same distance, right? So what's interesting is the torque. So if I add that to both sides, you can see that the torque by Fa equals the torque by Fn plus the torque by Fb. And what does this mean conceptually? It just means the torque by this wire needs to balance out the torques by Fn and Fg. It has to be a greater torque to balance out two other torques. Well, what this means is the torque by Fa has to be greater than the torque by Fb, right? Because it needs to balance out torque by Fb and Fn. So that means that the force Fa times R needs to be greater than Fb times R. And you could see, hey, if they have the same distance, the force needs to be bigger. So in other words, if one torque is bigger than the other and they act the same distance apart, then the force, that's the only way the torque can be bigger is if the force is bigger. So hopefully that kind of makes sense. Fa is going to be greater than Fb, so I can even update my my little thing. There's other ways to look at it, right? You could choose an axis of rotation right here. And what that shows is, okay, from this axis of rotation, it's going to be the length of the beam plus Fg, right? And then so the torque by Fa needs to balance out these two torques, right? When you're looking at this axis of rotation right here. And when you look at this axis of rotation, Fb needs to balance out the torque by Fb needs to balance out these two torques. But at this axis of rotation, Fn actually produces a smaller torque because it's a closer distance. And so therefore Fb would be a smaller torque because it's balancing out less. There's multiple ways to look at it depending on your axis of rotation, and I'm going to talk about that in the next few problems. Really quickly though, determine the force exerted on 300 Newton board with two wires A and B if the box is a mass of 15 kilograms. So box is a mass of 15 kilograms, and I got to determine the force exerted on the 300. So determine the force exerted on the 300 Newton board by the two wires A and B. So I gotta find each force basically. So this is where you gotta choose your axis of rotation. I can't even use this torque net equation because there's two unknowns, right? There's gonna end up being these two torques that I don't know. So I have to now switch to a new axis of rotation. And if I change my axis of rotation to this one, look at that. Sorry, I redrew what I just erased. Oh my God, I'm so silly. So if I put my axis of rotation here, Fb produces no torque. So if Fb produces no torque, that gets rid of an unknown for me. So now I get the torque by Fa minus the torque by Fg minus the torque by Fn equals 0. So I would get Fa times, so let's say the length of this board, it gives us to it, it's fine. So I'll say length of the board, right? Because it's acting the whole length away. Equals, so if I add them to both sides, we get torque by Fg plus torque by Fn. So Fg That's the weight of the board. Now, what distance from this axis of rotation does it act? It acts half the distance, right? Because center of mass is in the middle. L over 2. Plus torque by Fn. Fn acts 2 meters from point B, right? So that R is going to be 2 meters. So I get Fa 3.5 meters equals 350 newtons. 3.5 divided by 2 is, I think, 1.75 meters. Plus, and then Fn by the box. Well, the box is, does it say? Oh, 15 kilograms. So I was like, oh my god, I really hope. So 15 kilograms. I'm going to use 10 again for my own sanity. Newtons per kilogram times 2 meters. And then solve for Fa. I guess I don't know if I can use my head. Do I not have a calculator? Do I seriously have none? Nope, no calculators? I swear I had one there. I swear. All right, just solve for Fa. Sorry I can't give you a conclusive answer. When I did this all those years ago, I got, I don't know. I don't know. Use a calculator and solve for Fa. That should be your answer. Maybe I'll put answers in the comments, maybe, once I'm done with this. FB, and then for FB, you just use your Fnet equation, right? So Fa plus FB equals Fn plus Fg. Hopefully you can see why, right? Because if you do Fa plus Fb minus Fn minus Fg, and add the downward forces to one side. Now you know Fa, you know Fg, you know Fn, you can solve for Fb pretty easily. So, let's go on to the next one. 2 more. I mean, not 2 more, but, 2 more with different parts, or at least 2 more scenarios. So, this diver one, this one, took me a while. When I was taking the class, it took me a while to, wrap my head around it. But if you have a diving board, right, and you're trying to draw an FBD for this person who's about to jump off, and there are these support bolts right here, right, and you're trying to draw an FBD, your first instinct might be, okay, for my FBD, clearly they're both pushing up, right? These 2 support beams are both pushing up. FG pushes down, and I should label these. I'll call them FA and FB again. And we have the Fn by the diver. Pretty easy, right? However, if our axis of rotation is right here, right? I'll draw it in the middle. Hey, you get rotation, right? These 2 point up, this points down. This is not in static equilibrium. So what gives, right? Honestly, the best way to approach a problem like this is just do it like yourself. So if I put my axis of rotation right here, there's going to be no torques, and the way I do that is by pushing down, so you don't get any torque. There's this Fn, right? So I need something to balance this out. So in fact, what you get is if you put one support beam, okay, let's do it like this. You put your 2 fingers as your support beam, right? You can see naturally there needs to be something keeping it down. If I did it like this, and then I push down, well, that's gonna fall down. How do I keep it in static equilibrium? I need something to keep it down, like so, right? So I get a scenario like this. I get a scenario like this where one is pushing up, but then this one is pushing down. If I were to erase that, I get FB, or I get FA like so. How do I, how would I conceptually see that? Well, you got to think about each axis of rotation. At this axis of rotation, this torque, but the torque by FA would balance out these 2 torques, right? At this axis of rotation, the torque by FB would balance out these 2 torques. And you could see with your fingers which direction the torque is. At this axis of rotation, this torque balances out these 2 torques. At this axis of rotation, these 2 torques balance out this torque. So it's like you could check at every axis of rotation and make sure is my thing in static, like, is it even possible for my thing to be in static equilibrium? And then hopefully you realize this force will be way bigger. Suppose you were given a value for the force on the board by post B, and you were asked to find the mass of the diver. Where would you place your axis of rotation? Place it right here, right? Because I know the force by this post. I'm trying to find the mass by the diver, and I know the mass of the board. I can get rid of one unknown by putting my axis of rotation there. Write a torque net equation. So based on this, the torque, so which way is clockwise or counterclockwise would be FB, right? So torque by FB minus the torque by FG minus the torque by Fn is going to equal 0 Newton meters. So now we can just solve, right? So FB times R is going to equal FG, so R1 times FG times R2 plus Fn times R2. And I'm finding the mass. Okay, it's fine. We'll leave it like that. So we're given mass of the board and the value of that force. Find the mass of the diver. So I need to find the mass of the diver. So what I can do is just really, I don't even need to do it like this. I can do it add Fn on both sides. So minus and then equals right here. 3,700 newtons. That distance from the axis of rotation for post B is 1.6 meters. FG by the board, which was 23 kilograms times 9.8 newtons per kilogram time minus what? Minus something. Wait, what am I doing? Fn, right. Oh, wait, length. That's what I'm doing. I'm sorry. I'm getting scatterbrained. Length would be half the board, so it's 2.5 meters, right? Because it's half the distance, so that would be 2.5 meters. It's going to equal Fn, which is what I'm solving. I'm finding the mass of the diver, so it'd be mg, right? So m 9.8 newtons per kilogram times the length, which is 5 meters, right? Because it's acting at the very end. The force, at least. That's what I mean. You can solve for m. I got 110 kilograms. Don't trust that too much because I probably got this wrong. But if you do this equation and solve for m, that should be your answer. So determine the force by post A. Now that you know this force, and Fn, you can use your Fnet equation to solve for Fa. And I'll put the answers in the comments because I just don't have a calculator right now. Okay. Well, I don't know what noise it just came out of my mouth. Sorry about that. Okay, last one is some sort of beam bell problem. So we have a hinge, and you have a beam, you have a bell. How do you draw bells? Try like this, why not? So, boom. Wow, what a bell. Hopefully you guys can hear the music downstairs. Are we just drawing? I think we're just drawing no, we're solving too. Draw an FBD. So we're trying to find the tension in the rope. So this beam has negligible mass. Bell's gonna be pulling down, tension's gonna be pulling up. So what will the force look like here? Well, if this was your axis of rotation, right, the bell, there's no FG because it's negligible mass. So this force will be causing rotation this way. I need a force that's going to be supporting that. Cool. So now we just got to find the tension in the thing. So let's use our axis of rotation right here because I'm not given anything about the hinge. So torque, this would be clockwise or counterclockwise would be clockwise. So torque by Ft minus the torque by the bell is going to equal 0 Newton meters. So Ft times L, the total length, is going to equal the weight of the bell times 2/3 the length. So we're not given the length of the beam, that's fine, it cancels out. So Ft is going to really equal 2/3 the weight of the bell, which is 120 newtons, I think. So that should be about, what is that? Is that, it's 240 over 3. Would that not just be 80? Yeah, isn't that just 80? Why did I say 83.3? Oh, it's 125. Alright, so it's I guess 125 times 2 is 250. It's 250 over 3, whatever that, I think it's 83.3. Yeah, so hopefully this video was of some help. I know it's a little long, but this worksheet's long. So blame your teachers. Thank you for watching. Hopefully this made torque make more sense, as the kids say these days.